All right. So we want to welcome everyone to chemistry seminar, ChemSem. And today we are going to have a really important and relevant topic. To introduce our speaker is Dwain Park, and he's a senior biochemistry major here at Andrews. And his hometown is right here, Berrien Springs, Michigan. He plans to attend Loma Linda University for medicine after graduation. Are you going to go directly, or are you going to do something before that?
Directly. I don't have any plans.
Oh, okay. And he spends his free time playing with cats and sleeping. I find that pretty interesting. I don't know, because isn't cats famous for sleeping?
Oh yeah, just napping with the cats.
That's what I thought. That's what I thought. Napping with the cats. Anyway, John, it's your turn to introduce our speaker.
Thank you, Dr. Murray, for the introduction. I'll be introducing our speaker, Kathryn Perrine. Dr. Kathryn Perrine earned her Bachelor's of Science in Chemistry from the University of Carolina in 2004. During her time as an undergrad, Dr. Perrine worked with Panman dendrimers to ER and EU dope phosphorus, exploring spectroscopy and surface chemistry. Dr. Perrine obtained her Ph.D. in chemistry from the University of Delaware in 2011, focusing on molecular level surface chemistry by studying reactions on functionalized silicon surfaces. Before joining Michigan Technological University, she was a postdoctoral scholar at the University of California, Irvine, and a visiting scientist at the Joint Center for Artificial Photosynthesis at CalTech, researching liquid and vapor interface solutes for atmospheric research using electron-based techniques and photoelectrical mechanisms. Currently, Dr. Perrine is an assistant professor of chemistry at Michigan Technical University. Her research group focuses on surface chemistry of complex interfaces, emphasizing earth-abundant metals and oxides for addressing environmental and energy challenges. She has 17 years experience as a surface scientist and enjoys teaching surface chemistry to K-12 and postgraduate level students. Today, she'll be discussing the surface chemistry of iron surfaces and their interaction with disinfectant byproducts to address issues with water quality and the remediation of contaminants. Please join me in welcoming Dr. Kathryn Perrine.
Thank you. Very good.
All right, thank you so much for the lovely introduction. Can everyone see my screen?
Yes.
Okay, I guess raise your hand if you have a question. I guess we take questions at the end, right? Okay, so thank you so much for the kind introduction and the invitation to speak. I'm excited to teach you about some of the cool things that we're doing in our lab and how that impacts corrosion and water quality. Let's see, how do I? Right. Can everyone see my second slide? Okay, great. And so one of the things, first of all and foremost, I want to point out the team of graduate and undergraduate students that participate and really do a lot of the research that goes on in my group. In fact, I want to point out my graduate, Chithura de Always and Dr. Mikhail Trout, who have done a lot of the work with corrosion, PM Iris, at the air-liquid solid interface. And they worked with a team of undergraduate students, Julia Lundeen, Alex, and Kaylee War. My current team of students, now that these students have moved on and graduated and gone on to do amazing things, is that my current students who are working on our project on water disinfectants on iron, Subhash and Richard are graduate students, and they were teamed up this summer with Drew, Danica, and Ryan to work on some of these complex interfaces. And so we think about corrosion and infrastructure. Climate change has really impacted and really put a strain on our infrastructure and resources. So when we think about climate change, we know that from rising levels of CO2, this has impacted all different disaster events such as droughts, wildfires, flooding events, and winter storms. You can see here over a period of time, this has increased drastically. And we know that this is costing us a lot in our infrastructure, and particularly for corrosion, it's costing $2.5 trillion, not including environmental consequences, which is putting a strain on our public drinking water systems across the United States that ultimately result in several main breaks per year from corrosion of these pipeline systems. And it's estimated that trillions of dollars are going to be needed to replace these million miles of pipelines. Unfortunately, though, we have a bipartisan infrastructure law that's investing in trying to upgrade and replace some of our infrastructure. The ones I want to point out to you that are particularly interesting are replacing our lead pipes within the water system. Another one is investing in better roads and bridges and investment in environmental remediation, among others. In particular, one of the goals of this law is to bring a safe drinking water to American households across the United States and back to schools. And so you can see here the effects of climate change as well as the investment in infrastructure. We really need to start paying attention to the chemistry that goes on in our water pipelines and how this impacts our health. And so when we think about water and clean drinking water supply, we have to ask ourselves, where does that really come from? So our water system shown here comes from our rivers and streams in our natural environment, and that water sources goes on through a treatment plant where pathogens and viruses are disinfected. And ultimately, this treatment plant then stores this water and then is ultimately distributed through water main lines down through service lines into our household, schools, and buildings. And so this is kind of the pathway that our water takes as it goes through these water systems. And so when we think about these pipelines that come in contact with the water, there's lots of different chemistry that's happening in these water systems. You can see here a glass of pure drinking water that's very clear, but ultimately there's lots of things in here that we can't see with our own eye. Ions, bacteria, pathogens, and those get treated with disinfectants, but can also form byproducts from those chemical reactions, along with metals and inorganics. And so as a surface chemist, we kind of take a very fundamental approach to try to understanding how these chemical reactions occur on the surface of these pipeline systems that ultimately can affect our health as well as we consume some of these things. And so what are the pipelines made out of? Well, typically the older systems are made out of lead pipes, but they can also be comprised of galvanized steel or zinc-coated steel, copper, as well as plastic lines. Now, this is what your pipeline looks like when it gets installed, maybe in the basement of your house. You can actually go down and look if you have access to that. But when you cut open a pipeline that's been used after some time, it might look something more like this, where we have corrosion and the growth of biofilms on the surface of these water pipelines. And so we have to ask ourselves, how does the chemistry of this occur on these different systems? And when water comes in contact to it, how does it react with the surface of these systems? Now, when you cut open a system like this, you might think that there's actually corrosion happening. But when we think about corrosion on these different materials, not all corrosion is equal. Depending on the potential of corrosion of these different materials, some metals are unreactive, such as titanium, or not as reactive. But as you move down this trend, you can see for like copper, brass, cast iron, and zinc, as you go down this map, you can see that some of these materials actually corrode quite easily. And there's different types of corrosion that can happen on the surface of these metals, such as uniform corrosion, pitting corrosion, and all kinds of things. But fundamentally, we have to have an understanding of what these corrosion reactions are doing, and chemically, how are they interacting with the water system. And so when we think about chemical reactions in the water system, when we input water through these pipelines, they can undergo lots of different chemical reactions. We implement disinfectants such as free chlorine and monochloramine to disinfect the viruses and pathogens that are in here. But ultimately, these can react, form stable biofilms and inorganic scales that build up on the surface of these pipelines. In addition, depending on where the water source is coming from, the pH can increase or decrease, which can then increase metal dissolution and also decrease the scale stability. And the inorganic scale that coats these pipelines is known to protect the pipes from further corrosion. But one of the case studies which we try to avoid, but we also look back at this as a learning experience, is from the 2016 Flint water crisis, where the city ended up switching the water system, and due to the lack of a corrosion inhibitor and high amounts of chloride, this ended up corroding and allowing lead dissolution into the water system, severely affecting the health of a community. And so ultimately, iron also ended up in this water system. You can see here from the photograph, when you have a high amounts of iron, it actually discolors the water system. And ultimately, we ended up with a drop in pH, higher chloride concentration, and there were no protective phosphates protecting this lead from dissolving into the solution. And ultimately, over time, this can lead to complete failure of the pipeline system. Ultimately, you could get cracks and crevices that ultimately lead to flooding events and things like that. But we use this as a case study because there's lots of lead pipes around the United States that need to be replaced. And so we try to understand the chemistry that goes on these pipelines to avoid other types of disasters such as this. And so when we think about water disinfection, water disinfectants are added to the water in order to treat pathogens, bacteria, and viruses. So what exactly is disinfection? So we use a strong oxidant known as free chlorine, or basically sodium hypochlorite. And this is commonly known as the household bleach. And so when you dissolve bleach in water, we can all smell this when we clean our bathrooms. The hypochlorite ion reacts with water to form hypochlorous acid. And in an equilibrium balance, this goes on to react to form other types of chloride in the system to form dissolved chlorine and ultimately chlorine gas. And so this is what you smell when you clean your bathroom or your appliances in your house. There are other types of treatment that aren't quite as oxidizing, such as ozonation and UV light treatments. I'm not going to talk too much about that, but there are other ways to disinfect your water system. A secondary let me back up for a second. One of the downsides of using free chlorine to disinfect the water system is that free chlorine can react with natural organic matter to form disinfection byproducts known as trihalomethanes or haloacetic acids. And so here I'm showing an example of an alcohol like natural organic matter that when it reacts with hypochlorous acid, it can go on to react to form haloacetic acids and trihalomethanes. And you can see here the list of them. There's actually limitations on how much of these can be in our water system because consuming too many of them over time can actually cause cancers and other types of things that we don't want to experience. And so a secondary disinfectant that we can substitute for the free chlorine is known as chloramine. So it's not as strongly oxidizing as the hypochlorite. And so therefore we get a reduction in the trihalomethanes and the haloacetic acids due to the fact that it's lower redox potential. So it's a longer lasting disinfectant. But the downside is it can also decompose to form NDMA and actually corrode other metals such as copper. And so one of the goals of our newest project is to understand the reaction of chloramine on these iron interfaces if, for instance, this water would come in contact with minerals in the water system or the pipeline surfaces. So I'll talk a little bit about that as well. And so our group is interested in looking at the chemistry of iron surfaces. And so why iron? So as I mentioned, iron is ubiquitous in our industrial infrastructure as the main component of steel. So steel is basically an iron carbide that has iron present in it, iron is present in there, but also iron is present in the natural environment in the water and mineral cycles, where it's in soils, minerals, and it can also make its way into the atmosphere, where the dust can undergo photochemical reactions affecting the climate there. But in this water and mineral cycle, oxidation reactions can occur, ultimately affecting other reactions in our water system. And so this is another reason why we want to study iron, because it's present in the natural mineral cycles, and also the fact that it's a known catalyst within these systems. One other interesting thing about iron is one of the 5th most prevalent metal oxides in the natural environment. And so because it has such a high prevalence, there is a need to study these systems on a deeper level. Okay, so fundamentally, what is corrosion? It ultimately involves reduction oxidation reactions on iron surfaces. So for instance, if we take a piece of iron metal and dip it in a water solution, the anode, or at the anode, the iron will undergo oxidation to form iron 2+ and 3+ species, releasing electrons into the water system. And then those electrons will then go on to react at the cathode with water and oxygen to form hydroxyl species. Now, over some long period of time, those species react to form iron hydroxides as well as iron oxides on the surface of these materials. And this forms this signature orange color, which we colloquially know as rust. So in the environment where there's no liquid water, but maybe water vapor, over long periods of time, bridges and these infrastructures can rust, but it's on a much slower rate. Now, if we take a piece of iron and put it in a salty solution, the ions from the salt solution will actually speed up the reaction and corrode the sample very quickly. So here I'm showing a piece of iron. And if we dip it in a sodium chloride solution, you'll see the sample has changed color to this yellowy color and this orangey rust region at the interface. And so the way we approach to understanding these reactions in complex environments is we know that there's several different oxidation states that can exist on these iron materials as they naturally undergo oxidation. Now, the iron 2+ sites are known to have high reactivity, but the 0-valent iron sites are known catalytically in biochemical reactions, as well as the Haber-Bosch process, which we use ammonia in fertilizer. But ultimately, these reactions in the pipeline are very complex because they involve the presence of solids, liquids, and gases simultaneously. And in the presence of these ions and pathogens and disinfectants can all undergo chemical reactions, all while the surface of the pipe is transforming from a metal to an oxide. And so we as surface chemists take a very big step back, and we try to look at the reaction from a very fundamental and simplistic approach. So what we do is we can model the system on an atomic scale using a pure iron crystal. So if we cut the crystal along the 1-1-1 face shown here in this model, we can expose active sites on the surface where we know the precise location and the distance of these iron sites with respect to each other. And therefore we know the surface that we're starting off with, because every site is equally the same. Now, if that surface oxidizes, let's just say to a magnetite surface, so an Fe3O4 surface, we end up getting a combination of iron 2+ and 3+ sites on the surface, along with oxygen active sites. And then so this can significantly change the reactivity. And so the approach we take in my group is to understand the chemical reaction on a very pure system, on a pure iron surface with a pure solution, and try to understand that reaction before we move to a more complex system, such as the one that's actually found in the pipelines. And so the way we do this is we use a surface chemistry approach to measuring these complex chemical reactions, specifically on metal oxides that are earth abundant, such as iron. And so what we do is we can use a variety of spectroscopy and microscopy techniques in order to probe the surface chemistry at the liquid-solid interface and measure how the analyte reacts with the surface and how the surface undergoes changes. Now, what we can do is we can slow down that reaction by placing our iron crystal in a vacuum system, and we remove all the air and component gases out of that system, and we can controllably expose the vapor phase of our molecule of interest to the surface and then watch the reaction happen under a very small amount of that. And so we can connect reactions at the gas-solid interface with the liquid-solid interface to try to understand these very complex reactions. And so in my group, we use a variety of surface analysis techniques in order to understand the surface chemistry. So we use the spectroscopy to tell us the chemical changes on the surface and microscopy to tell us the physical changes. And so we need both of these to completely understand how a surface undergoes a chemical reaction. And so not any one single surface technique is going to give you an answer about the full chemical reaction. We as scientists have to use our little microscopes in order to look at a very small part of the surface that we can't see with our own eye, using these techniques to help us see the surface as it undergoes those changes. And so the two techniques I'm going to talk about today that we spent a lot of time on is surface infrared vibrational spectroscopy, as well as atomic force microscopy to study surface corrosion. And if you're not familiar with infrared vibrational spectroscopy, what it is, it's a technique where if we probe our surface with infrared light, the molecule that's adsorbed to the surface, if it has an active dipole moment, will undergo different vibrational motions that we can see in our spectrum. So for instance, if our molecule is excited by infrared light, we can have a symmetrical and asymmetrical stretching, or we can have bending modes such as scissoring and wagging. And these different modes will appear in different regions of the infrared spectra that we can use to find the chemical signature of that particular species and the orientation at which it reacts with the surface. So how do we actually do these experiments? So for instance, if you take a substrate and adsorb a film to it, and you transmit infrared light through this ultra-thin material, some of that light is absorbed into those vibrational modes, and the rest of the light is transmitted. And so we know this from the Beer-Lambert law, where we can detect the absorbance modes or vibrational modes of what's on the surface and relate that to the thickness of the material and the concentration. So for instance, we can essentially subtract out what the substrate is by only looking at what is absorbed on the surface using this relationship. Now, this particular configuration isn't necessarily surface sensitive. This is what you could use to use FTIR to look at solids, gases, or liquids. To get a surface sensitive technique using infrared spectroscopy, we have to use the physics laws or the refraction of light. And so the refraction of light is defined as when a light beam comes in, interacts at the interface, and then is refracted away because of the index of refraction of the two different media. In this case, it's air and water. And this is demonstrated if you look at this glass and the straw that's in this glass, you'll see the light is refracted and the straw looks disconjointed because of the light is refracting at that interface because of that. Now, if we have a specified angle, and depending on the index of refraction of the two media, we can actually get a total internal reflection of light at these interfaces, depending on what those refractive indexes are. And so we can use this phenomena in order to probe the top layers of a surface using a surface sensitive configuration. So if we come in with our IR beam, it goes through an optically active crystal such as germanium or diamond. It interacts with our iron surface and then is refracted out. We can essentially probe the top few microns of the surface using this configuration and get surface sensitive information of our adsorbate reacting with the surface. Another type of configuration that uses this reflection mode is known as infrared reflection absorption spectroscopy, or IRIS. And so the way this works is if you polarize the light between P and S polarization, and it reflects off the surface at some kind of angle, and then it's detected by the detector, you're able to probe the top layers of the surface if you use a high grazing angle of incidence. So that means this angle is somewhere around 80 to 90 degrees. But one of the things about this particular setup is that you have to provide a purged environment around here, because as we know with infrared spectroscopy, we can detect gases as well as liquids and solids. And so I'm showing here the gas phase spectrum for water. We have water stretching and bending as well as carbon dioxide in the natural air. And so we have to purge out this environment around it with nitrogen or dry air in order to remove these modes, so we can see the very, very small surface sensitive modes that are on the surface. And this can us to lower the penetration depth to less than a micron. Now, one of the advantages that has been developed in the past couple decades is we can actually get around even using a purge box in order to purge out the water vapor and CO2 from around the surface. And this is called using a polarized modulated infrared reflection absorption spectroscopy. And so the way this works is, again, you take the linearly polarized light, but you use a photoelastic modulator to flip between the P and S polarized light. And so the P polarized light stands for parallel light component to the that is parallel to the plane of incidence, and the S polarized light is perpendicular to the plane of incidence. And so if you flip between these two modes in a fixed frequency, the light interacts with the surface, it goes through the detector, and then that signal is demodulated. You can essentially subtract out that gas phase contribution without ever having to use a purge box, and you can take a spectrum in a single way instead of having to take a sample and a background. All right, and so this ends up resulting in, instead of absorbance, our signal then becomes a differential reflectance mode, where we have the difference of the P and S signals divided by the sum. And so what an example spectrum of what that looks like, so this is an iris spectrum on a gold film on a glass substrate. As you see, we can see the IR spectrum, and we see no traces of water vapor or CO2 in our spectrum. We just see the background signal of gold is a perfect reflector and doesn't form an oxide in air. And so the shape, you'll notice the shape of this looks more like a rainbow. This is what's called the background Bessel function, right? And so one of the things our group did is we utilized this technique in order to look at 3 phases and 2 interfaces simultaneously. And so we used the PM iris method at the air liquid solid interface in order to do that. And so what we do is we take a polished iron sample and we pull a meniscus layer right on the surface. And we come in with our infrared light, probe that very thin meniscus layer, and that light gets reflected and focused back to the detector. And we can essentially look at both the air liquid and liquid solid interface at the same time. So here's an example of that, where we have the gold spectrum shown in yellow. And if we dip that in an ethanol layer, you'll notice the signal is reduced to this blue spectrum. But then we also see these very small peaks on top of our background Bessel function for the CH stretch and CO stretch from liquid ethanol. And so this shows that we can use this technique to look at both the air liquid and liquid solid interface simultaneously. And so what we did is we used this technique in order to look at the corrosion reactions, which we basically treat as a spontaneous oxidation reaction using this method. And so we developed a 3-stage approach in order to do that. So what we do is we take a polished iron surface, expose it to a diluted electrolyte, in this case hydrochloric acid. We pull our meniscus layer and we probe that surface through the air liquid solid interface. And so what we do is we just collect a variety of vibrational spectra as a function of time. And then over some time, we remove some of that liquid layer. And this it thins the ultra-thin film liquid layer at our analysis spot, and this allows for atmospheric oxygen and CO2 to absorb to our interface region, allowing for oxidation to begin slowly. After we collect more spectra, after some time, we completely remove the liquid layer, allowing oxygen or the spot to completely oxidize, and we form this rust strip shown here in red. And so here's some example spectra of that experiment where so this is of stage 2 when we were gradually removing the liquid layer, we're allowing the sample to oxidize, and you can see here that the OH bending mode grows in as a function of time. And eventually the peak-to-peak signal goes back up, meaning that we've removed that liquid layer from our analysis spot. And then once we get to stage 3, we see a very sharp iron oxyhydroxide mode that we can attribute to lepidocrysite. And that's exactly what this red strip is shown in stage 3. So in this way, we can watch the surface corrode as a function of time using our surface vibrational technique. All right, so back to the chemistry. So one of the things we wanted to do is to look at different salty solutions of ions that are commonly found in the water system, particularly sodium and calcium. And so what we did is we did an experiment where we exposed an iron surface to a diluted sodium chloride electrolyte, and we can watch the evolution of hydroxyl bending and carbonate stretching modes appear as we oxidize the surface. You'll notice in calcium chloride that signature, the position of the peaks and the shape is much different for calcium chloride. So we can see here that a different type of film is being grown on the surface in these two different solutions. Now, if we take the peak area under the curve and plot that as a function of time, we can essentially get the rate of carbonation and hydroxylation on these two different surfaces. And what you'll notice is that in calcium chloride, we have a much faster rate for hydroxylation and carbonation compared to that of sodium chloride shown here. And so we thought this was pretty interesting. And so we can follow on looking at these different spots using our ATR FTIR technique to complement some of our PM-IRIS measurements. So here's the photographs from the experiments. And what you'll notice is that at the interface region, we observe the formation of this white film on the surface for both calcium chloride and sodium chloride. Now, the region that was completely submerged in solution, which we can't probe with PM-IRIS, but you'll notice we formed this rusty film that's on the surface. These are obviously two different types of films. And so when we analyze the interface region, so this top region that was exposed gradually to atmospheric oxygen and CO2, we observe the formation of these very strong carbonate stretching mode that aligns nicely with the signature of these natural mineral specimens. So the sodium chloride, the sample in sodium chloride has a similar signature to what we observe for siderite or an iron carbonate film. And the iron sample in calcium chloride forms a carbonate film at the interface that matches with that of two different polymorphs of calcium carbonate, aragonite and calcite. Now for the portion that was not gradually exposed to air, so this rusted region, if we look at that with our ATR technique, you'll notice that we get exactly the same signature on the surface, indicating almost exactly the same film has been grown. We see a very sharp peak indicative of an iron oxyhydroxide mode, which agrees with that of the mineral lepidocrysite. And we also compare that with goethite, a different polymorph of iron oxyhydroxide. And you'll notice that the vibrational signature doesn't match as well as it does for lepidocrysite. So we can say here that we grew lepidocrysite in the submerged region in a cation-specific carbonate film at the interface region. And now this was interesting to us because you'll notice in our solutions, none of these solutions have carbonate in them. And so we kind of scratched our heads and we were trying to figure out, why is this happening? Well, it's known that carbon dioxide can dissolve into solution at the air-water interface quite quickly, forming carbonic acid and also carbonate ion. And so this is what we think was happening in these two different solutions. And so we did a control experiment where we used the same time frame to run a PM-IRIS experiment for iron in nanopure water where there were no ions. And sure enough, we don't observe any carbonate film formation when there are no ions, even though the sample is open to air, where CO2 can dissolve into solution. And so one of the hypotheses was for that was that it's known in the corrosion literature that chloride ions can pit through the surface, thus allowing for reduction oxidation to occur easily. And if you're not familiar with this concept, most metals in air can form what's called a native oxide layer on the surface. And so that native oxide layer tends to protect the surface from other types of chemical reactions. Well, we believe what happens is the chloride ions pit through that native oxide layer, exposing nucleation sites and also dissolving iron into solution, thus allowing for the bicarbonate to react with these different sites, growing the carbonate film. And so we wanted to investigate the physical changes of how this corrosion is happening in agreement to corroborate our PM-IRIS experiments. So we turned to using atomic force microscopy in order to understand those different physical changes on the surface. So if you're not familiar with atomic force microscopy, the way this works is we use a tip, a nano-sized cantilever that's tracked by a laser that's reflected off of it to a photodiode. And essentially what we can do is we can scan across the surface, and the tip kind of tracks the position of the surface as it goes over the hills and valleys of the sample on the nanoscale. And you can essentially construct a three-dimensional image of what the surface topography looks like using this surface sensitive technique. And so my first graduate student, Mikhail Trout, and undergraduate Julia, got together and they decided, let's look at corrosion and track that as a function of time in order to see how these physical changes happen. So these are actually very difficult experiments. I'm going to show you the results here. What they did is they just took the cantilever, placed it in a droplet of solution, and they just sat there and imaged over a large area, over a small area as a function of time. And what you'll notice is that in calcium chloride, you see this pitting that occurs after about 42 minutes, and those pit sites tend to increase and become much more prominent after a couple hours. Now in sodium chloride, you'll notice the pitting occurs, but it's not as drastic as with calcium chloride. And so one of the things that's interesting is that we have twice as much chloride in this solution as we do in this one. And so that could be a reason why we actually have more pitting on this surface. But one of the other things we can do to quantify our data is we can essentially collect the root mean squared, or the standard deviation of the roughness of this surface. So here we're showing the XY image, and then this scale over here shows the height scale of the different corrosion sites on the surface as it roughens. And so if we collect the root mean squared of each image and plot that as a function of time, you'll notice that for the calcium chloride has a 3 to 5-fold increase compared to that of sodium chloride. And this just shows that the calcium chloride solution is corroding much faster than the sodium chloride, thus providing those nucleation sites for film growth. One of the other things the students did is that once they removed the liquid layer and allowed the sample to oxidize in air completely as it was drying, what they saw was really interesting. And so what they found is that the surface is no longer flat or filled with little pit sites. It actually grew these interesting mineral morphologies on the surface that look very similar. So on the top row, I'm showing calcium chloride. The bottom is sodium chloride. You'll notice these stringy-like features agree with that signature for lepidocrysite. And these hexagonal platelets that we observed at these dilute concentrations, we actually see this very small carbonate, and we think this is from an iron hydroxycarbonate species on the surface. So you can see here how we can connect the surface topography with our infrared spectra on the surface to help us understand the chemistry and the physical changes of how a surface corrodes and grows mineral films. And so the mechanism that we can piece together from this is that we have the chloride ions pit through that native oxide surface, which thereby initiate the corrosion, where iron dissolves and ultimately undergoes reduction oxidation. Over time, the ions in solution can aggregate and of course react with the bicarbonate that dissolves in solution, ultimately precipitating on the surface. And after the solution is removed, undergoing oxidation in air, we nucleate and grow these unique mineral films on the surface. And so this is what we think is happening in a pipeline system, is that these unique solutions are really playing a strong role with these other dissolved species, these dissolved gases, to form these unique carbonate and corrosion films on the surface. And so this just shows you how just by simply changing the ion or the number of ions can severely impact the physical and chemical changes of what you're doing on the surface of your pipeline. Okay, so I'm going to switch gears a little bit and talk more about chemical reactions. And so one of the things we wanted to understand also is we have all these different oxidation states that have high reactivity with these different species in air and also in solution. And as I mentioned, the zero valent iron sites are catalytically active for the Haber process, which we use for ammonia formation. But these are also sites that are active for dehalogenation. And so this is just showing 3 different types of mechanisms for dehalogenating the disinfectant byproducts I mentioned earlier, where we want to remove the halogen species, thus making the disinfectant byproduct more benign, so we don't consume that particular component in our water system. And so in order to understand the reaction of how this happens, what we can do is we can simulate these types of chemical reactions in our vacuum system at the gas-solid interface in order to really understand how the molecule decomposes and undergoes a chemical reaction with an iron surface. So what we did is we took an iron 111 surface and we exposed it to the vapor phase of a model disinfectant byproduct known as chloroform. So CHCl3, and we also exposed it to different amounts of water vapor. And we can use our spectroscopy techniques in our vacuum system in order to measure how these different chemical components react on these different sites. And so here's a picture of our vacuum system. What we do is we put the crystal in our vacuum system, we clean it inside in a very, very low pressure, and we can focus our light source through the window in our vacuum system. It goes through a single bounce in a reflective mode, just like I showed you earlier. And then that IR reflection is reflected off into the detector. And we're able to detect the different chemical species as the molecule adsorbs to the surface. Right, and so here's an example spectra of this particular reaction. What we did is we cooled the surface down to minus 118 degrees Celsius. And if we expose the surface to, in this case, CdCl3, where we replace the hydrogen with deuterium, and we can watch the chemical signature change as we increase the exposure. So going from 5 Langmuirs, we notice the only chemical signature we observe is this very small species down here, which is the CCl stretch. But as we increase the exposure from 50 Langmuirs to 100 Langmuirs, we can observe the formation of the CD stretch, the CD bend, and other types of carbon chlorine modes, indicating that the chloroform is adsorbing to the surface. If we zoom into that CCl stretch region, you'll notice at very small exposures, there's just a little bump here showing that the chloroform has interacted with the surface, but the shape of these peaks and the signature is changing as a function of coverage as we increase the amount that we're absorbing to the surface. And so we think this is interacting with the surface at very, very small exposures. And one of the ways we can measure whether or not the chemical is decomposing is if we heat up the sample up to room temperature from minus 110 C, we can watch the vibrational features disappear. So you'll notice here the CCl stretch. This is what we started with at 100 Langmuirs. And as we increase the temperature, we'll notice those modes disappear. And so one thought is, okay, maybe the chloroform is just desorbing from the surface. Therefore, no chemical reaction has occurred. But another possibility is that if it undergoes decomposition and the CCl bond is broken, then we'll no longer actually see these vibrational modes. And that's exactly what we see is with another technique, we're able to measure the amount of chlorine species on the surface. And what you'll notice is that after we heat the sample to 25C from 118, you'll notice the chlorine species is still present, meaning that we've broken these bonds, the molecule is dissociated, but now we can't see those vibrational modes in our infrared spectral range. And so this shows that the chloroform, a simplified model of a disinfection byproduct, will undergo dechlorination at room temperature on a pure iron surface. And so this is known in the natural environment where halogenated hydrocarbons can undergo reductive dechlorination at these zero valent iron sites. You can see here a variety of different trihalomethanes that are capable of undergoing dehalogenation on iron, which is used as a catalyst here. And then finally, the last project I want to highlight is our newest project that we're working on, is on the interaction of monochloramine with iron surfaces. And so monochloramine is produced from the reaction of aqueous phase ammonia with sodium hypochlorite in a basified solution. But it's not that simple to just study pure monochloramine on iron, because all these chemical components will actually be present in small amounts because there's a reverse reaction between monochloramine and an aqueous system, especially at high concentrations. And so, so one of the things that we're studying is how these different chemical components interact and corrode the surface individually, so we can understand completely how this reacts with the surface. And this is critical to understanding the mechanisms of disinfectant byproduct reactions and improving water quality. And so when we think about the chemical signatures of these different chemicals, there's a lot of overlapping vibrational modes that make it difficult to study. You'll notice that some of these chemical components, such as NH4Cl and monochloramine, have the similar NH bending mode and OH bending mode. And so my undergraduate students have really worked a lot this summer to try to understand these chemical signatures and how they react with iron on the surface. In addition, we're also turning to, in addition to our surface analysis techniques, we're looking at other types of methods in order to understand the aqueous phase reactions as well. But one of the things I want to point out is this photograph here of our samples that is reproducible, that the monochloramine at the interface forms that signature rust strip, but there's also all these other different spots on the surface indicating there's heterogeneous corrosion going on. You notice this looks drastically different from the samples in the calcium chloride and sodium chloride samples. And so we're working to understand how all these corrosion products can occur on iron from the reaction with monochloramine. And so one of the things my students did this this summer is we got involved with our Michigan Tech Summer Youth programs, where the students got to explore how different metals corrode in different types of solutions on these surfaces, and how and trying to connect that with water quality. And so my undergraduate and graduate students had a great time doing these experiments with the K through 12 students. Okay, so what we learned about these reactions at complex interfaces is that corrosion at the liquid-solid interface, the pitting's necessary for the nucleation sites of carbonate film formation, and that we also get carbonates are grown that have a specific cation effect at the air solution iron interface that are influenced by the type of cation in the electrolyte, and that the rate also depends on this film growth. At the gas-solid interface, we can slow down the reaction on surfaces to really measure how something decomposes and reacts with these different surface sites, particularly for the model DBP on iron 111 as it undergoes dissociation on zero valent iron. And then finally, we try to, what we're trying to do is connect what we know about these simplistic systems to more complex systems, such as the reaction of monochloramine and the disinfectants on iron, and how those mechanisms affect water quality. And so I encourage you guys, if you have one takeaway message to think about when we think about pipeline corrosion and all these complex things going on. As from a surface chemistry's perspective, how would we answer those questions if we know these simplistic reactive sites that are undergoing changes in this complex system? Right. So I hope I've inspired you and shown you a little bit about this complex surface chemistry and water pipelines and how it relates to water quality. So I'd like to thank the National Science Foundation for funding, as well as the Michigan Space Grant Consortium for some of the work on the mineral films, as well as our collaborators at the museums. And then, of course, our other collaborators at our chemistry department and shared facilities on campus. And of course, the students, they do all the work of the data that they're shown here. One of the other things I want to pitch is that we really, you saw that in my group, we have a lot of undergraduate research going on. And I just want to point out that our chemistry program has personalized education with small class sizes, where we really want undergrads to get hands-on research for hands-on lab experiences. And we have multiple degree options for our bachelor level students here. And we also have a graduate program, an accelerated master's program at Michigan Tech Chemistry Department, where the students get to work with the undergrads on all this state-of-the-art equipment to do research. So if you have any questions, please reach out to me. And I just want to point out, last year, we also became a bridge partner with the ACS Bridge Program. So I'm happy to answer any questions about that. And so thank you so much for your time. I guess let's see if there's any questions.
Okay, thank you so very much for your presentation. John Juan, do you have any comments, questions to lead us off?
I have a question. I don't know if this was answered or I just need more clarification. So you did find out that, there's some interaction with the iron and with some of the compounds like chloroform, was it? So does that mean that the buildup of rust is actually helpful, or should we investigate more to find out if there's other interaction?
So you're talking about how do we dechlorinate the disinfection byproducts from corrosion? That's a great question. So zero valent iron isn't really present in the natural environment by itself. You have to either allow it to undergo reduction, or it can be produced by corrosion from corrosion sites in those little pit sites. And from there, we can produce the zero valent iron sites that can undergo reactive sites for the dechlorination reaction.
I see. I guess that's true. Oh, you can go ahead, Dr. Murray.
No, finish your thought.
Sorry. I guess that's pretty interesting because we think of rust as kind of bad, but it seems like this is actually can help us deal with some compounds.
Yeah, exactly. Yeah, rust is bad in the sense that if it undergoes too much degradation, the material can become brittle and then break apart, or you can punch holes in your pipeline and things like that. But when you think about providing zero valent iron sites for dechlorination, in this case, we're using it to remove harmful contaminants from the water system.
So the follow-up is this already out commercial? Are people using zero valent iron?
Yes, it's been known for a while now, but one of the things we wanted to answer with our study was the exact chemical reaction of a simplified disinfection byproduct, such as chloroform. We know in reality these disinfection byproducts, such as the trihalomethanes, are much bigger. And so to measure a larger molecule on a surface is really complicated. And so what we do is we can shrink down the size of the molecule to something very simple, so we can look at the individual thermodynamics and kinetics of the dissociation in a simplified system. But yes, it's been known for a while.
Okay. So I know earlier you were wondering if some of these topics were covered in general chemistry. And so we have two general chemistry profs here with us. Are some of these topics, I assume that they are.
I can speak real quick, and thank you for that exciting talk. I just wanted to point out real quick. So I'm from Michigan, and there was two places I was going to do my undergrad. One was at Michigan Tech or Andrews University, and I ended up coming to Andrews. But a lot of my friends went to Michigan Tech, and I visited Michigan Tech, and it's beautiful up there. And it was nice to see some pictures of the students and things. So great work being done at Michigan Tech. And I was surprised that you actually had a picture of my service line from our house to the city line. So you had that picture there. I don't know how you got that. Yeah, so we do touch base a little bit on corrosion. As with most topics in GChem, it's a glancing blow. We kind of maybe a day on it and try to hit on some of these topics. I wish we could spend more. It's actually pretty interesting, and it's something that affects our lives on a daily basis. So it's not as much as I would like to, but I think about that with most topics.
I would say there's pictures, I think, that you got from the CNE News. There was a CNE News article from that time frame of what happened in Flint, and it has the little pictures, and those are actually in my Gen Chem slides. So I have a little comment on how the, you know, and it's actually really nice because it's an intersection of the solubility chemistry, because they chuck the phosphate in because phosphates are very insoluble. And then the chlorine, then it oxidizes up the lead that was exposed when the phosphates were gone. And then I think also, I wonder also if it can make complex ions with lead as well, right? Because you can make all those, like, you know, chlorine, and that gets even more lead in the water. So anyways, yeah, we definitely mentioned corrosion. We've got students that can testify if this was true or not, or they remember any of it. But
yeah. One thing I like to tell students is that the issue of corrosion, you know, it's been investigated a lot by the material science community, but from a chemistry perspective, you know, maybe we could take, and that's the take my group is looking at, is we take a different approach to looking at that. A lot of corrosion is measured using electrochemical methods, but we're using chemistry to really identify the corrosion products on the surface, which is the other part of the equation, you know, and so it takes a lot of, you know, collaboration between material scientists, civil engineers, chemists to really solve this issue of water quality and corrosion. There's a lot of complex things going on there that I think we should take another look at, because we can really help solve a lot of problems that way.
So
yeah, right. I mean, the surface chemistry, or the spectroscopy that you were doing there was also, you know, instructive to, as you say, it's not, I mean, it's a spectroscopic molecular identification rather than kind of the bulk phase electrochemical properties. So
yeah, that's one of the things that impressed me is the use of these instrumentation. So with the IR, do you have to modify, you buy a commercial available IR, do you have to modify it, or do you
Yeah, so the way so you can buy a commercial benchtop IR instrument, and we designed our own sample holder in order to do the reflection, the PM iris reflections. You can buy all the optical components separately. It's just they're not all in one package box like some of these I forget what they're called. These little sets that you can buy that you can just plug into the IR and use. We had to design our own setup on our optics table in order to get the right measurement, and it did take some trial and error. It actually took several years of work to get those first mineral films, but it's not super complicated to set up like some of these nonlinear optical techniques. I know they have a lot of laser alignment and tuning and things, but this is pretty much just optic alignment. So, but we don't use a high powered laser. It's just a basic benchtop IR.
Okay. All right.
And I can talk more about that offline if you have more questions.
Okay. So does any other student, any other person have a question? We could take probably another one.
I just wonder if there's any big takeaways already for, I mean, corrosion is going to happen. I mean, is there any way to just slow it down, or anything that you're learning now that the students can take away, or that you would, you know, if we could change things about how we deliver water even?
Yeah, there's a whole field of people looking at corrosion inhibitors. How do we provide a corrosion layer, a protective layer to grow that some kind of film that protects against the corrosion, or to prohibit that. So that's what I would say. There's still a field of work being done. I know at my institution, there's also people working on different stents and things in people's bodies. We have to think about not just corrosion on infrastructure, but also corrosion of devices and medical things in our body. It's a huge field in itself. So corrosion affects, you know, the health community directly as well. Mm-hmm.
So with us switching from lead to different materials, for the non-metallic ones, corrosion wouldn't be an issue, but there could be like bacterial problems with those. What is your understanding there?
So non-metallic materials,
So
like plastic,
PVC or something, pipes, yeah.
Yeah, I haven't thought too much about plastic, but I know having plastic dissolution into our water system is a huge issue right now. And I wonder, I'm sure it depends on the chemicals. You know, plastics aren't inert to everything. It's just a different ball game than metals are. And I wonder if, you know, over time, plastics could dissolve as little pieces into our water system, like some of these other plastic bottles and things that end up and these microparticles.
Yeah, microplastics.
But I think that would be you know, a chemical compatibility test to see how different plastic components react with acids and bases. Especially, they're not immune to corrosion, I guess, because the definition of corrosion is a removal of mass loss. And so if you have dissolution of small microparticles of plastic, I mean, that would definitely be another area of interest, in my opinion, especially if we're switching all our pipes to plastic.
Yeah, yep. So whatever the switch, we will still need surface chemists to figure it out. All right. Well, we want to thank you again for very interesting and relevant and like stuff that, you know, happens all around us. Chemistry is everywhere. Thank you so much. And we wish you continued success in your research. I noticed that one of your papers just came out this year too, 2023.
Yes, it did. Yeah.
So continued success in your work.
All right. Thank you so much for the invitation, and I enjoyed meeting everyone, and thank you for hosting me. It was a pleasure.
All right.
Thanks for joining us.
Okay.
All right. Have a good one.
You too. Bye-bye.